Hi everybody. First thing is I'm glad I have my glasses back so that I can actually turn on the video and do these recordings again. Uh, for about 4 weeks, almost 5 weeks, I didn't have my glasses, so my nose was right up against the camera because I couldn't see the screen, so I had to disable my video. But now I can re-enable it, so I can now. Put my face on the in the video, and and some of you have said that it helps with your focus and concentration. So I am very glad that I have my glasses back, and then we can now um, get back to the way that we were doing things. Okay. So today we're going to look at rational function points of discontinuity. Now, a couple of things that deal with rational functions and these points of discontinuity is this. All right. One, first thing is, how do I identify zeros? Well, we know that zeros are where the function crosses the x-axis, correct? Where the function crosses the x-axis, otherwise known as where the functional value is equal to 0. Okay, where is the function 0? Well, the function is 0 for the values of x, right, that cross, for the values of the x that make y equals 0, right? When the function is 0, your x values are your so-called zeros. Okay? Values of x which make the numerator, and if you look at the function, if you look at the rational function, it's basically the values of x which make the numerator go to 0. Okay? The values of x which make the numerator 0. Now we have something called vertical asymptotes. Vertical asymptotes are these vertical lines, all right, where it seems that the function diverges. The function splits apart and it separates. So instead of being a nice continuous curve like up here, right, where everything is kind of connected, the function all of a sudden, let's say, goes up and then disappears, and then it reappears from the bottom. There seems to be a gap here, an infinite gap. We call that an infinite discontinuity, or otherwise known as a vertical asymptote. Okay, so the x values are the vertical asymptotes that create this. It's a line, basically. It's an imaginary line. X equals some number. So in terms of the function, the rational function, the values of x which make the denominator go to 0. Okay, so the values of x which make the denominator 0, they're called vertical asymptotes. And we're going to abbreviate that using VA. Finally, these removable discontinuities or point discontinuities, they are basically holes in the graph. So you may have a nice smooth graph, but all of a sudden, at a distinct value of x on the graph, there's a hole. There's no y value associated with that x value. So it's undefined, in other words, at that value of x. And we call that a removable discontinuity or point discontinuity. In terms of the function, we have these when the factors that create vertical asymptotes and zeros as well, when we have factors that create vertical asymptotes and zeros cancel out. They cancel each other out. Okay, so in those instances, we're going to have what's called a removable or point discontinuity. Again, it's when you have factors in the numerator and denominator which were possible zeros and vertical asymptotes, they cancel out. If that happens, we instead have what's called a removable discontinuity or holes. All right? Okay, so now we know those three things. Let's go and see if we can figure out whether we have zeros, vertical asymptotes, or removable discontinuities. The first step in doing these problems is we have to factor. So let's factor. All right. So if we factor the top, we have x plus 4, x plus 4. And if we factor the bottom, we're going to have x plus 4, x plus 2, like that. Okay, now let's do our analysis. What are the possible zeros? The possible zeros. Again, possible zeros are where the function crosses the x-axis, or in terms of a function, where the numerator, the values of x that make the numerator 0. We have x plus 4, right? We have two of them, so I'm just going to write 1. X plus 4 is equal to 0, so x is equal to negative 4. All right? So this is a possible, not saying it is, so far it's a possible 0. We have to check the other stuff. All right? So at x equals negative 4, we may have a possible 0 where the function crosses the x-axis. What are our possible vertical asymptotes? Well, again, possible vertical asymptotes are where the denominator, values of x that make the denominator 0. We have two of them, x plus 4 and x plus 2. So let's check to see what are possible vertical asymptotes. X equals negative 4 and x equals negative 2. Here are possible vertical asymptotes. Now I want you to look here. Didn't we just say we had a possible 0 at negative 4? Now we have a possible vertical asymptote at negative 4. Guess what? We now know that there are factors in here, right? Identical factors. So automatically it should ring a bell saying, aha, those are going to cancel. What are our possible removable discontinuities? Okay, removable discontinuities where we have the identical factors, right? So here we're going to have x plus 4 over x plus 4 and x plus 2. Okay, so let's do it. Is there anything that we can cancel, top and bottom? Absolutely, it's the x plus 4s, right? So those two are going to cancel, which means these two are now gone. So what do we have? At x equals negative 4, we have a removable discontinuity at x equals 4. Okay? The removable discontinuities take precedence over either zeros or vertical asymptotes. So we have a removable discontinuity, a hole. We have a hole at x equals negative 4. So we have a hole at x equals negative 4. All right? And the only other thing we have is a vertical asymptote at x equals negative 2. Like that. All right, and let's check. And that is correct. Again, when we have a removable discontinuity at the same value as we do for the vertical asymptote in zeros, the removable discontinuity always wins. Okay? Let's take a look at another one. All right, so here we have this function and we're checking these three values. So we're going to have x plus 8 over, and let's factor this guy in the bottom. Okay, that's pretty easy, right? It's going to be x minus 9, x minus 1, correct? So let's do our little check. Possible zeros. Again, possible zeros where the numerator equals 0. So x plus 8 equals 0. So x is equal to negative 8. Here's a possible 0. All right. Number 2, possible vertical asymptotes. All right. Where are possible vertical asymptotes? Where the denominator equals 0. Okay, here's one, and here's the other, right? So we have a possible 0 at x equals negative 8, and we have possible vertical asymptotes at 9 and 1. And finally, let's check for possible removable discontinuities. All right. Well, in this case, we don't have any like factors in the top and the bottom, so there's nothing to cancel. So our conclusion is we don't have any removable discontinuities. No holes, right? These are holes, correct? We have none, no holes in the function. So let's select our choices. At negative 8, we have a 0, and then at 1 and 9, we have vertical discontinuities here. And that is correct. Okay, let's do a couple more. Again, first step, always factor. So we have, this is a difference of two perfect squares. So x plus 9, x minus 9 over x plus 9. Okay? Step 1, possible zeros. Set the numerators equal to 0. X plus 9 is equal to 0. X minus 9 is equal to 0. So we have possible zeros at x equals negative 9 and x equals positive 9. Okay? 2, possible vertical asymptotes. Possible vertical asymptotes. Okay? So set the denominator equal to 0. So x equals negative 9. Right? That's a possible vertical asymptote. However, as I said, the removable discontinuities take precedence. So in this case, it looks like we have common factors of x plus 9, correct? So these guys cancel out, which means we no longer have this and we no longer have this. So we have a removable discontinuity at x equals negative 9. Okay? There's a hole at x equals negative 9. Right there. All right? And then we have just this left. We have a 0 at x equals 9. And that is it. Okay, one more. Same thing. Factor. So we have x minus 7 and x plus 3. On the bottom we have x plus 13. Correct? Check. Possible zeros. Right? So again, set the numerators equal to 0 and solve for x. X equals 7 and x equals negative 3. So here are two possible zeros. Check for possible vertical asymptotes. Possible vertical asymptotes. Okay, so x plus 13, set the denominator equal to 0. So x is equal to negative 13 is a possible vertical asymptote. And 3, check for removable discontinuities. And in this case, again, we don't have like factors on the top and the bottom. So we have none. There are no holes. So let's put our answers in. 7 and negative 3 are zeros, and negative 13 is a vertical asymptote. And voila. Okay, guys? All right, take care.